So let's look at how we can make logic gates and enhancement load that are neither NAND nor NOR, but are bigger and do more complicated functions. In both the NAND gate and the NOR gate, we had a network consisting of two transistors, two NMOS transistors that were both drivers. This is the general architecture we will be using for any gate from now on. There will be a network. This network will be called the pull-down network, and in short, PDN. The pull-down network will be responsible for connecting the output node to ground conditional on a number of inputs. The PDN will consist of n NMOS transistors. Each and every one of the NMOS transistors will accept a logic input. So there will be a number n of logic inputs going into this pull-down network. There will also be a single diode connected load ML at the top. So let's look at how to make a logic function. First of all, how to identify what logic function is performed by a certain network, and then how to implement a certain logic function that is given to us. We will understand how this works qualitatively in this video, and then we will develop a more quantitative or analytical model of it in the upcoming video. So let's, for example, look at this network, which is the easiest kind of complex logic function we can implement. And so we have here A, B, and C. And the question is, what is the logic function implemented by this network? What is F? Now, when we had two transistors in parallel at the bottom, in the pull-down network, we got F equals A plus B all bar at the output. And when we had two transistors in series in the pull-down network, we got F equals AB all bar at the output. So what seems to be happening is the function we observe at the output is a function that represents the connections in the pull-down network, where every series connection is an AND and every parallel connection is an OR, except that at the end there's also an overbearing, like universal inversion that is applied to everything. And therefore the output of this logic gate is AB plus C all bar. And so why do we observe this final bar? Why do we observe this final inversion upon everything? We observe it because the architecture of the logic gate is based on an inverter. And so there is a final inversion that is imposed upon it. If we had started with a buffer, if using a single transistor in the pull-down network would have given us a buffer, then we would not have had this inversion at the output. So let's consider what we do when we have the opposite. That is to say, we are given a function, and let's make the function a little bit complicated. Let's make it a little bit nasty looking, and let's see what we can do to implement it. So now we are asked to implement this logic function in enhancement load. So there are a number of steps that we can follow to systematically do this. First of all, we obtain the expression of F bar. So we do not work with the expression of F. We work with the expression of F bar. In this case, fortunately, there was a huge bar over the entire thing on the other side. So F bar is equal to AB plus BC plus DE. Then, if there are any simplifications, if there are any logic simplifications that can be done, they should be done. So in this case, for example, taking B as common in the first two terms is something we have to do because it will simply save on area. It will save us a transistor in the pull-down network. Then we take the expression of F bar and we implement this expression using NMOS transistors, where every AND is translated into a series connection and every OR is translated into a parallel connection. And so we have B in series with A and C, both of which are parallel with each other, right? So this is one branch in the pull-down network. But this whole thing is then parallel with D and E in series with each other. And so we have another branch with D and E in series with each other. And at the top, we never forget to put our diode connected load. And what do we get at the output? So we implemented the connections of F bar. But there is another bar, another dash, another inversion that the architecture imposes. And so at the output, we get F. So if we implement the connections suggested by F bar, we get F. If we implement the connections suggested by F, we get F bar. So that makes sense, right? There is an inversion that is added by the architecture just by virtue of the fact that we are based on an inverter. And so let's take another example. This time around, we do not have a cooperative expression. So we do not have an expression where there is an overbearing bar over the whole expression. Instead, let's say we want to implement F equals A, B bar, plus CD, plus E, for example. So this is an expression that is devoid of bars, actually. It is very sparse on inverted input variables. And so we will follow the same steps. We get the expression of F bar, and this time we have to use the Morgan's theory because we have to expand the bar over the whole thing. And so remember, the Morgan's theory says that we can distribute an inversion on a bracket just as long as we change all operations to the opposite operation as we distribute the inversion. So each series becomes a parallel and each parallel becomes a series. So this is the expression of F bar. We take this expression of F bar as it is. Don't worry about, this is inverted or this is non-inverted for now. Just implement it the way it is. And so we have E bar, and E bar is in series with a bunch of other things. So it's in series with C bar and D bar, both of them being parallel with each other. So it's in series with a block with C bar and D bar. And these are series with a block with A bar and B, right? And this connects us to ground finally. Let's just notice that the choice to put E bar at the top, or the block with C bar and D bar in the middle, or the block with A bar and B at the bottom is for now up to you, because it doesn't really change anything. The function will be the same however you choose to distribute these transistors. There's always a diode connected ML at the top, and the output is taken at the source of the load. So then we get F at the output. The question is now, what is the number of transistors in this logic gate? And this question it depends on one thing that should be given when we are given the problem, which is, are the input variables and their complements available without additional inverters? If the answer is yes, then you will only count the transistors in the main gate. If the logic inputs are not available in true and complement form without additional inverters, then the fact that you are using E bar, for example, means that you have to use an inverter to get E bar. And you have to count the transistors in these inverters. So every single inversion is going to be an inverter. And what kind of inverter? It has to be an enhancement load inverter, because that's what it means to work in a logic family. It means that inputs come from the outputs of a gate from the same family. And so the number of transistors here depends on whether or not input complements are available without additional inversions. If they are not available without additional inversions, then we have to count the number of transistors in the main gate as well as transistors in the input inversions. So the main gate is always going to have n plus 1 transistors in the main gate, where n is the number of input variables that make an appearance in the expression that we implemented. So if we look at the expression we implemented, it had 5 appearances, A bar, B, C bar, D bar, and E bar. And so we have 6 transistors in the main gate. And then we have plus 4 input inverters, each of which will consist of 2 transistors. So 4 then times 2 transistors. There was another option to implement this logic function that would have been a lot better. If we took the expression of f and implemented that, so we have a and b in b bar in series, then c and d in series, then e bar, and then e finally in series, and this is the PDN, and there is always a load at the top. In this case, at the output, we do not get f, because we implemented the expression of f bar of f. We do not get f at the output. Instead, we get f bar. And so we have to use an inverter, an output inverter, to get the expression of f. And so f is actually obtained using an additional inverter, an additional output inverter. But what is the number of transistors here? We still have 5 plus 1 transistors in the main gate. We have one input inverter, so we have one input inverter giving us 2 transistors. This is used to calculate B bar. And we have one output inverter. So when we implement the expression of F, we get F bar. We need an output inverter that always consumes 2 transistors. And so we need 6 plus 4 transistors. Whereas using this method, implementing the expression of F bar, we would have needed 6 plus 8 transistors. So this means we have saved 4 transistors already. So which approach should we use? Should we implement the expression of F or the expression of F bar? It all depends on whether input variables are available in true and complement form and how the expression of the function looks. If input variables are available in true and complement form, it is always best to implement the expression of F bar and get F at the output, because that saves you the output inverter. If the input complements are not available with additional transistors, then you have to look at the expression of the function f. For example, a function like this, a bar, b bar, c bar, plus d, e bar, versus a function like this, a, b, c, plus d bar, e. So these two functions are very similar, except that the first function, f1, is rich in inversions. And so when you take the expression of f1 bar, it's going to be a plus b plus c into d bar plus e. So that expression is going to need one additional input inverter, which is useful. It's certainly a lot more useful than implementing the expression of f1, which would have needed 4 input inverters plus an additional output inverter. But if you look at the expression of f2, if you implement the expression of f2, you will need the main gate plus a single input inverter plus an output inverter. But if you try to implement the expression of f2 bar, you will need 4 input inverters and the main gate. So which is better is always determined by the prevalence or lack thereof inversions in the original expression of the function.